In this video, I will talk about simple panel data models in R. Before you watch this video, please make sure that you have watched my other video called Simple Panel Data Models. I have opened up the R script here and I have downloaded the two data files that we're going to be using today. I have put them in this directory that we're going to be using, and I have run the script, and the results are here in the console window, which I put to the side for you to see. So what we're going to talk about today is difference in differences model, and then we will also talk about panel data model with first differences. So before we're starting, we make sure that we install certain packages, and then we make sure that they are up to date as well. So in order for us to do the difference in differences model, we will be using house prices example. So here the example would be an incinerator, a garbage incinerator is built in a neighborhood. So what kind of effect would that have on the prices? So obviously building a garbage incinerator in a neighborhood would have expected negative effect on the prices, but we want to check that with the model. So let's go ahead and read in the data set. So we're going to be using this data set and we're going to read it into our data frame. And then we would be selecting several variables for us to use. And then we would see the structure of this data. And then we will use Stargazer to summarize the data. So what we have here is 321 observations for variables, and this is how the first few observations of the data look like. So we would have here, these are the house prices for these different houses. We have whether or not the house is near the incinerator, so 1 if it's near the incinerator and 0 if it's not. Year 81 would be equal to 0 for the year before and 1 for the year that is 1981. And then Y81 times near the incinerator would be basically a multiplication of these two dummy variables. So this is what, again, the mean. So the average price for these different houses is $82,721 that was sold. Whether or not it's near the incinerator, 29% of the houses were near the incinerator, and for 44% of the observations, they were in the second year, 81 versus the year before of 78. And then this is the multiplication of these two variables. So that's the average for that. Okay, so now what we want to do next is summarize house prices near and far from the incinerator in the before and after period. So again, we have two periods, before and after, and whether or not the houses are near and far the incinerator. We first want to get some descriptive statistics for that. So from the data frame that we have up here above, we want to first group the data by, and we're going to be grouping it by near the incinerator, and then also by year 81. That's the dummy variable. And then we want to summarize it. So we're going to be using these variables. And so for the variables, we're going to use R price, which are the house prices, and these functions. So for our list, we're going to be having mean, and we're going to be picking up the mean. And then we're going to pick up the length of these series, and we would call this observations. So these are the results that we have here. So we're grouped the data by near the incinerator, and if year is equals 81. And then we're summarizing the house price, the mean, and how many observations do we have. Okay, so if we have a house is not near the incinerator and in the before period here, this is the average price, 82,000. If it's not near the incinerator and it's in the after year, we have 101,000. If it's near the incinerator in the before period, we have 63,000. And if it's near the incinerator in the after period, we have $70,000. So what visually here we can inspect is that basically if we look at the second period, so the first period in comparison to the second period, and that's the first period in comparison to the second period, we have that the house prices are increasing in both for both those that are near the incinerator and not near the incinerator in the before and after period. And we also see that actually house prices, if they're near the incinerator in the after period, are lower than if they're not near the incinerator. But we saw this trend also in the before period, that house prices for those that are near the incinerator are lower than those that are far from the incinerator. So again, the question remains open. Did building of the incinerator reduce house prices? So this is what we want to answer here. So let's do it first the slow way, and then we would be doing the difference in differences model. So how we're going to approach this is we're going to be running two separate regressions. The first one will be in the after period, after building the incinerator, and the regression in before period, before building the incinerator. So here we would be using the house price regressed on near the incinerator, and then from this data, we would be subsetting the data if year equals, and we're using double equal sign here, 1981. So this is in the after year of 1981. And here in the before year, we would be picking up this model here, updating model 1, update model 1. If the subset, but for the subset, we're going to be using year 1978. So this is the before year. So here we had the after year and we're going to update it with the before year. And so we can summarize this and we could pick up the B1, the coefficient on the near incinerator here, and B2 we are going to call the coefficient on near the incinerator in the other model. Let's see what we get here. So this is the regression in the after period that we have. And so the way to interpret it here is that in the after period, we have the houses that are near the incinerator are about $30,000 lower than houses that are far from the incinerator. Now, in the before building the incinerator, when the year was 1978, we have that the houses that are near the incinerators, that's the coefficient here, are about or $19,000 less than houses that are far from the incinerator. So now, if we actually record these two coefficients here, the coefficient that we have B1 on this model and B2, and we take the difference between them, we would be having minus 11, minus $12,000. So this is the difference in differences effect. So what we are finding here is that in the year after, house prices are $31,000 lower if they're near the incinerator. In the year before, we have the house prices are 18 or $19,000 lower. So if we do this one minus this one, that's going to be the $12,000 here. And that's going to be by how much prices for houses that are near the incinerator were lower in the after period versus the before period. So this is one way in which we can calculate the difference in differences effect. So another way in which we can calculate the difference in differences effect, because we have two differences, is to calculate to estimate a regression for the treated units, the ones that are near the incinerator, and also for the control units that are far from the incinerator. Here we would have as a model the house price regressed on this dummy variable if the year is in the after year, 1981. And we would be doing this for the houses that are near the incinerator. These are the treated units. And for the houses that are far from the incinerator, these are the controlled units here. So we're going to be updating this model 3 that we have above for the controlled units here. So if we estimate this model and we get the coefficients now, these are going to be the coefficients that we have here. So here we have the house price regressed on the after dummy variable on the after period. So here we would have that for the treated units, we would have that house prices increased by about $7,000 in the after period. But for the controlled units, the ones that are not near the incinerator, we have that these house prices actually increased by about $19,000. So if we do this coefficient minus this coefficient, we would be getting this differences in differences. So what we would get is that the house prices in the for the treated units are going to be $11,000 lower than the house prices for the controlled units in the after period. So here is this difference in differences effect that we have. So notice that this number here, the differences in coefficients is exactly the same number as the difference in coefficients right here. So again, the difference here is that we have a regression in the before period, in the after period and the before period, and then we pick up the coefficient on the near the incinerator and we subtract these, or we can have it alternatively the treated regression for the treated units and the controlled units. Um, and then we can pick up the coefficients on the after period and subtract those, and we're going to get the same result here for difference in differences. So whichever difference you do first would not matter. Now, this was the slow way of doing things, so let's do it the fast way. The fast way would be to estimate a difference in differences regression. So how we are going to do this from now on is we need to include three terms. One of them is treated. One of them is a dummy. This is a dummy variable for whether or not the unit is treated or control. After is a dummy variable for whether it's the after or before period. And then we have an interaction term of after times treated. So here we have that the house price is regressed on near the incinerator. So that's our treated uh, dummy variable. Then we have y81. This is the dummy variable for the after period. And then we have the interaction of these two terms. So any difference in differences model needs to have these three terms here. So once we estimate this model and summarize it, the coefficient on the interaction term here would be that difference in differences effect that we see. Okay, so this is that coefficient on the interaction term. So here we have house price regressed on near the incinerator, dummy variable for the second period, and the interaction term. And these are the different uh, coefficients that we have here. And this is the coefficient that we have on the interaction term. So notice that this coefficient here, is exactly the coefficient that we had here before, the difference in differences, and exactly this coefficient that we had before. So by design, we have this coefficient. The way to interpret this coefficient is that house prices that are near the incinerator in the second period are about $12,000 lower. Now, if we look actually at the p-value, this is not significantly different from zero, so that's also important to notice here. But the magnitude is minus $12,000. So, so in any difference in differences model, this is the most important coefficient. Now, if we look at these other coefficients, we could actually come up with the original summary statistics that we had for the data. So, for example, if we have that we're looking at the average house prices in the year before, so this dummy variable is equal to 0. And for the control unit, so this dummy variable is equal to 0, and the interaction term is equal to 0. This is the house price for them. Now, if we have a house that is near the incinerator in the before period, so we would have that this would be the intercept for it. So we basically need to sum up these two numbers. That's going to be the average house price. Or if we have a controlled unit, which means it's far from the incinerator, but in the second period, we would be picking up this intercept plus this to find that house price. So we can actually backtrack and find to the summary statistics and get them from these coefficients that we have here as well. And so again, this is how to do a difference in differences regression. And the most important thing is if we want to know, does building of a garbage incinerator reduce house prices in the second period? We need to build this difference in differences regression and look at the coefficient on the interaction term to say that whether or not these house prices are being significantly lowered. In our case, they're lower, but by $12,000, but this effect is not significantly different from 0. Okay, so next we are going to be switching gears and talking about panel data model with first differences. So in order for us to do that, we would be looking at a panel data. And so here we would have panel data for wages. So we're going to pick up the data set wagepan and then read it into our data frame. And for this exercise, we're going to only keep 2 years of data. So here we're going to filter and only keep the year if the year is 1980 or the year is 1981. And that's what we're going to keep here. And now also let's generate a dummy variable for year and an interaction term. So here, if the year is 1981, let's call this D of 1981. And then I also would like to generate an interaction term, which is this dummy variable for the year times hours. So have this variable ready to go. Okay, so the first thing to do is the data set doesn't have wages, it only has log wages. So let's go ahead and calculate wages from it. So to do that, I'm actually calculating as wage equals 10 to the power of log wage. Now you could do e to the power of log wage as well to get to the wage. But this is how I actually happen to calculate it here. So now let's go ahead and list, describe, and summarize the data. So here we would summarize the data by actually using the variables NR. So this will be an indicator for the person. Year would be the time indicator. And then we would have wage, which would be our dependent variable, total number of hours worked, number of years of education, and number of years of experience. So now we are going to be actually getting the first 10 observations of this data. We will see the structure, and then we will use Stargazer to find summary statistics for the data. So here's how this panel data, true panel data looks like. So one thing to notice is that the data that we had before in the example with the garbage incinerator was a repeated cross-sectional data. In other words, that the houses that are sold in one year are not necessarily the houses that are sold in another year. But here we have exactly the same people both years in the data. So here we have person number 13, 2 years of data for them. We have the wages and hours worked for the year and education and years of experience for them. So this is person number 17. Again, 2 years of data for them. This is the wages, hours worked, number of years of education and experience, and so on. Notice one very interesting fact. In this data set, it happens that, say, person number 13 has 14 years of education, person number 17 has 13 years of education, and so forth. But no one in the data actually happened to increase their years of education from one year to the next. It could have happened, but it just didn't happen. And likewise, if you look at the years of experience because they were working, it all deterministically increased by 1 unit. So in the next year, they had one more year of experience. So this is interesting to note because we would be summarizing these two variables later on. Now, here's how the data structure looks like. So here we have 1,090 observations for these 6 variables. And these are some of the summary statistics that we have here um, for the wage, for hours, education, and experience. Now, obviously, it's not meaningful to find the mean for the person ID or for the year. It's not very meaningful like that. So, and another thing is that when we're finding descriptive statistics now, these descriptive statistics are across the individuals and over time. So they're a mixture of the between variation from one person to the next and the within variation of like, how does this variable change over time for the same individual? So let's try to summarize the data in a different way using panel data methods. So for this, let's first look up the number of observations. So how we're going to do this with this data set, let's group by the person ID. So this is the cross-sectional dimension. And then let's summarize the number of observations here that we have. And so what we are going to get with this kind of summary is that the first person, we see that they have 2 years of observation. The second person has 2 years of observations. The third person has 2 years of observations, and so on. Or alternatively, we can now use the data set wagepan, group it by year, and now summarize here the number of observations and call it n underscore year, call it the number of observations, but we're summarizing now by year. So if the year is 1980, we have 545 observations, and if it's 81, we again have 545 observations. So now we talked about overall variations, between variation, and within variation for panel data here. And how the overall variation is a variation of each of the variable across, between individuals and within individuals. Here, the between variation is basically how does a variable vary from one person to the next, and within variation is how does a variable vary within the individual. So basically, for one individual, how does that vary over time for one individual? In order for us to calculate these statistics, let's select the data frame and then select these variables from the data frame. And so now let's use this function here, function x. And so what we want to do here is for each variable, we want to take x, which is um, the value minus the mean of x. And so this is how, and then as data frame, so basically use this as data frame, and then using Stargazer show the summary table, and we want to omit the summary statistic mean here in this table. So here's what we're going to have here. So these are the standard deviations here that we're very interested in. And the standard deviation again is showing how does each of the value differ from the mean. But this mean is calculated across all the individuals and over time. So that's why this is an overall variation. That's how this one varies. Now, for the between variation, what we're going to do is we're going to look in this data set, but then we're going to be grouping by NR with the individual ID. And so once we're grouping by a person ID, we would be selecting the same variables and we would be summarizing the mean as data frame. Then we're going to deselect this person ID and then we're going to summarize the data again. So basically for the between variation, these are the means that we have here. And what we've done is basically we grouped the data by individual and we basically calculated the means of this variables by individual, and we then summarized that data set here. So what these standard deviations here are showing is basically how does each variable differ from one individual to the next. That's the between variation, difference from one individual to the next. Finally, we have the within variation. So here what we're going to do is we're going to group by person ID again, select the different variables that we're interested in. But here for function x, we're going to be using x minus the mean of x. So this mean of x here is actually grouped by, we already grouped the data by individual. So this mean of x is actually the mean for each individual. So what we have here is that the value is of each of the variables here for an individual is minus the mean for this individual. So that's why this is a demeaning procedure where uh, each of the values is minus the individual mean for this person. And that's why we're showing here the within variation, because we're showing how does the data for each individual differ from the mean for this individual. And then, of course, we're just going to be summarizing this data set. So here we have, these are the variations that we have for each of these variables. And one of the very interesting things here to notice is that the standard deviation of the education variable is 0. So as I showed you, like as we looked at just the first 10 observations in the data set, it so happened that no one got additional education. So everyone in data set, whatever their education was, it stayed like that. So if we calculate the difference between a person's education minus the person's average education, that's going to be a 0, right? Because it doesn't change for the individual. And this is why this variation that we have here is a 0. Uh, Now notice that there is a between variation for education. This means that this variable differs from one person to the next. So someone has 12 years of education, another person has 10 years of education, and so forth. Um, Another interesting observations to have here is that, say for example, number of hours that are worked. So here we have 557 as standard deviation for the between variation, but for the within variation, we have 283. So what this tells me is that there is more variation that is between individual than within the individual. So that variable, how many hours you work in a year, is not as variable within a certain individual than it varies from one individual to the next. So the between variation is higher for this variable here. Okay, so now these are the different variations. So let's go ahead and now start estimating different regression models. So let's first just kind of explore the data a little bit and estimate different types of models. Here we would have regression model with both years in, ignoring that it's a panel data set. So what we're going to do here is estimate a model of wage regressed on hours, education, and experience. So this is the model that we are going to have here. Again, that is a model that would would be combining and pooling all the data together. In this model here, we see a negative effect of hours on wages. So another model that we can estimate here is just regressing wage on hours itself. So here we see a negative effect, but that effect is not significant of hours on wages. Another model that we can estimate is also putting here a dummy variable for the second period. So here's what we have. Here are the coefficients that we have. We're looking at this coefficient that we have here on hours, and this coefficient is significant. So more hours worked is associated with lower wages. We can also estimate we can estimate models for each year. So here we could be running the model for year 80 and then for year 81. So in the first period of 1980, if we are using the regression model of wage regressed on hours, we have that more hours worked does not affect wages because this coefficient is not significantly different from zero. And for the second period, we also have that this coefficient is not significantly different from zero at the 5% level. So now we can also estimate a model that has different intercept and slope for both years. So to do that, we can actually add a dummy variable for the second period and then an interaction between the dummy variable and hours. And so here, these are the results that we have here. The coefficient on hours, again, is not significantly different from zero. So these are all alternative methods that we can estimate with panel data. But from now on, we're going to be using panel data models when we see panel data. And so the first model that I wanted to introduce is what's called a first differences model. So in order to do that, let's first calculate first differences. So how we're going to do this is we're going to use function x, where this function would be, I would pick x minus, and I will use the dplyr package from this package, we're going to pick up the lag function of x. So what we're going to be using here is a value minus the lagged value of the same variable. So basically that would be a first difference here. And so here, for each of these, let's take the data frame wagepan, group it by the number, by the individual ID. So this is the ID for the person. And then we are going to calculate D wage, which would be the difference in wage. And so this difference in wage would be applying this function here to wage. So pick up wage, and instead of wage, when I say difference of wage, give me the value of the wage minus the lagged value last period. So that's what we call difference of wage, and we're going to call this new variable D wage. And same thing for education. Pick up education in 1 year minus the education the previous year. That take that difference, apply this function to education, and that's going to be de-education and so forth for all of these variables. So we're now going to put this back in the data set. And so now let's um, look into this data set, select all the variables, including these first differences that we calculated, and let's get to see the first 10 observations. So this is how the first 10 observations look like for these first differences. So notice how, say for wages, So I see the wage here, and so this is for person number 13, and that's the first year, and that's the second year. So this is the wage in the first year, this is the wage in the second year. So how do we calculate the first difference? Well, it's the value here minus the value in the previous period, and that is this value here, 55.5. So for the second person, 17 is the value 33 minus 47, and here we have minus 14.4, and so on. So notice how we have NA here for not available, and the reason for that is that we don't cross, from different observations. So you can't subtract this value of one person minus the value of the other person. So we can just subtract the first difference for each individual, but not across the individuals. And this is how the rest of this data set looks like. Notice very interesting that the first difference for education is always 0. Why? Because no one got more years of education. So we have 14 minus 14 is 0, 13 minus 13 is 0, 12 minus 12 is 0. And here is something very interesting, but experience varies, but it varies very deterministically. So if we do 2 minus 1, that's a 1. If we do 5 minus 4, that's also a 1. If we do 5 minus 4, that's also a 1. 3 minus 2 is also a 1. So even though this variable kind of for a number of years of experience varies from one individual to another, when we take the first differences, it's all ones for people because everyone increased their years of experience by 1 year. So these two variables are actually, because this one is 0 for everybody, this one is 1 for everybody, are going to cause problems because we won't be able to include them in the regression anymore. So now, if we attempt to estimate panel data model with first differences and we try to include all of the variables because of what I showed you here with the first difference in education and experience, if we try to do that, we would not be able to estimate the coefficients on these two variables again because these two variables are deterministic now. These two variables are collinear with the intercept and we cannot include them in the model. So now this is the only one that we can estimate in the model. So here's how to do it correctly. So panel data model with first differences, we're going to regress the change in wage to change in hours. To the first difference of wage, regressed on the first difference in hours, and this is going to be the intercept and this is going to be the coefficient on the first difference. And one thing that we haven't shown here, but this coefficient now here is significantly different from 0. So basically we have in this particular case we have that using first differences we show a negative relationship between hours and wage. So the way to interpret this coefficient is that if we actually, if a person increases the number of hours that they work by 1 hour from one period to the next, their wage is actually going to reduce by 3.5 cents from one period to the next. Okay, so this concludes the discussion on the first differences estimation of the panel data model.